Welcome everybody to the last session of the day and the conference. It's about succinct arguments. We will have two talks, and the first one will be about max proofs, succinct arguments for machine computation from vector lookups. And this is a work by Zijin Li, Lucas Xia, Wilson Nguyen, and Nirvan Tyagi. And Nirvan will give the talk.
Great. Thank you. So thanks for coming. Let me start by reviewing the goal of the setting of proofs for machine computation. So in this setting, we have a program that's defined using instructions over a fixed size instruction set. So you can think of this as what would be implemented by a CPU, for instance. And then when you run a program on an input, we get an execution trace that has the actual instructions that are run when executing the program on that input until we receive some output. And so I'll note that the sequence of instructions in the execution trace might differ from the sequence of instructions in the program description due to input-dependent branching logic, for instance. And so then our goal here is to allow a prover to be able to prove to a verifier the validity of an output with respect to a program executed on some input. So just introducing, again, informally, a little bit more notation here for the proof system. The public statement will consist of the program description, the instruction set description, the input and the output or commitments to each of these values, and then the witness consists of the execution trace. And so with all of this, again, informally, we want kind of the standard security properties for proofs. We want zero knowledge to hide the witness from the verifier. And this is especially relevant when we're talking about the committed input case. We're trying to hide the input and the input-dependent execution trace. We also want standard soundness properties. We don't want the prover to be able to trick verifiers into accepting incorrect program outputs. And importantly, in this talk, we're going to be looking at succinctness. So we'll be looking at the SNARK setting, succinct non-interactive arguments of knowledge. We want the proof to be small and fast to verify with respect to the instruction set size, the program size, and the execution trace. Okay, so proofs of machine computation have long been proposed as a way to outsource computation from low resource clients to high resource clouds in a verifiable manner. One new application is in the blockchain space that has kind of reinvigorated research on this topic. Blockchains like Ethereum support smart contracts, and they typically define these smart contracts over supported fixed instruction sets like the EVM, Ethereum. Hello, hello. Okay. Thank you. Okay. Okay, so for the Ethereum chain, these smart contracts are defined. I think I'm cutting in and out. Okay. Hello. Okay, great. Okay, so in this blockchain setting, when a new block is created, these smart contract transactions are included into this block. These transactions are just program executions of these smart contracts with some blockchain state and user provided input. To verify the validity of a block, these program descriptions along with the inputs are distributed to validators, and the validators simply recompute these programs, these smart contracts, to determine whether they're correct. So proofs of machine computation help in this setting for a couple different ways. One, the succinctness property allows us to replace distributing these programs across all these validators with just these succinct proofs. So we're saving on bandwidth there. And also the validators don't have to do this redundant recomputation of the smart contracts. They just have to do this succinct verification of the proof. Another way these proofs end up being helpful is in providing zero knowledge. instead of distributing these inputs across all validators as well, we can, and having these inputs stored on this public blockchain, we can consider smart contracts with committed inputs and enable new privacy-preserving smart contracts and new applications that can be run on top of public blockchains. So this is an exciting new setting. In this talk, I'm going to be discussing a new approach for proving machine computation proofs, with the goal being to improve prover costs. So why improve prover costs? Again, with this blockchain motivation, now the throughput of the blockchain, how many smart contract transactions it can include per time step, is going to be dependent on how fast we can produce proofs for the correct execution of these smart contracts, right? And so we want high throughput. We want to be able to support a large number of smart contracts to be included per time step. Okay, so let me start by just giving a high-level understanding of how I even aim to improve prover costs in this setting. So how we typically prove machine computation, execution occurs in these steps, where each step has two components to it that we describe as constraints for the proof system. So this first component is the control logic, which it tracks the program counter, determines which instruction we're going to execute in that step. It will read memory, read the register state, determine what inputs to provide to that instruction. And so techniques for creating constraints for this type of control logic fall under a line of work called offline memory checking. And so for the most part, let's just assume we have constraints for this type of control logic. That's not going to be a contribution of the work that I'm going to be talking about today. The second component of constraints for each of these steps is the actual instruction logic, constraints for the instruction. And in prior work, typically we prove constraints for the full instruction set at every instruction step, execution step. And of course, the prover costs are going to scale with the number of constraints that we're proving. So we might hope to do better than this. After all, at each execution step, we're only executing one of the instructions from the instruction set. So we might hope to be able to get away with proving just the constraints for the executed instruction rather than the full instruction set. This ends up being challenging for a few reasons. The executed instructions depend on the input, and they're not known ahead of time. And also, since they depend on the input, we need to hide which instructions were executed in the case of zero knowledge for the input. And so all of this is avoided in prior work by simply proving the constraints for the full instruction set. So actually, earlier this year, it was shown that we could achieve these prover costs. A couple of works came out that showed that we could build provers with these costs on just the order of the executed instructions using techniques from proof recursion, verifying proofs within proofs. And so what I'm going to talk about today in our work, we show that we're able to achieve these same costs, asymptotic costs, while avoiding recursion altogether. And what that means is that we also avoid some of the concrete prover overhead that comes with recursive costs as well. Okay. So that's the high-level plan for how we're going to reduce prover costs. The key cryptographic primitive that we design and apply to this setting is a succinct vector lookup argument. So let me first explain what a vector lookup argument is, and then how we're going to apply it to this machine computation setting. So, okay, here let me show just what a basic lookup argument. This is a field element lookup. We have two collections of field elements. You can think of the right one as a lookup table, the left one as a lookup result. We want to enforce the lookup relation. That is that every element in the lookup result is present in the lookup table. And then in our work, we're going to be looking at an extension of this. We're going to be considering vector lookups, where now the table and the result, instead of consisting of single field elements, we have vectors of field elements of some fixed size, m. And vector lookups aren't a new idea. They've been used before, and we have techniques for building vector lookups from element lookups. But in our prior work for building vector lookups, the proof size and the verification time scale linearly with the vector length m. So the proof size would be of size m, the verification time would be of size m. And so what I'll show shortly in how we want to apply vector lookups to the machine computation case, succinctness in this parameter vector length m is going to be important. Okay, so how can we apply vector lookups to the machine computation setting? Let me bring up the execution flow of machine computation. Let me simplify things for the purpose of this presentation. Let's not consider control flow, the control logic. And recall our goal is to prove constraints for, instead of the full instruction set at each step, we just want to prove constraints for the executed instructions. So I mentioned before, the constraints for these instructions we can typically represent as a vector of field elements. So here I'm describing each instruction as a vector of size m. And then in typically how we prove snarks to achieve succinctness, this full vector of constraints that represents, say, the executed execution trace is preprocessed by the verifier in a setup phase to, for example, encode this vector of constraints into a polynomial commitment that can then be used by the verifier during verification for succinct verification. So again, the challenge in our setting is that the verifier can't do this preprocessing since the constraints for the executed instructions aren't known ahead of time. They can't be preprocessed. So our idea is, okay, we can't preprocess the constraints for the executed instructions, but we can preprocess the constraints for the fixed instruction set. This is known ahead of time. So we can build this instruction set table that encodes the constraints for all the possible instructions. The verifier can preprocess this, and then during execution, we can build up these execution constraints on the fly and prove that the execution constraints are valid using a vector lookup from the instruction set table. So then once we have this execution table, we can largely rely on prior techniques from snarks to get a succinct argument from this execution table of constraints. Okay, so I'm skipping a few steps here. For example, I'm not showing, I don't have the control logic here. We don't have to just show that every instruction in the execution table is pulled from the instruction table, but we also have to show that it's the right instruction that we're looking up, right, with respect to the control logic. So I'll refer you to the paper for those details. But this is the high-level strategy of how we want to apply vector lookups to the machine computation setting to get our prover efficiency requirements. In the remainder of the talk, I wanted to give a little bit of insight in how we're then able to build this succinct vector lookup. Okay. So now you can kind of see why succinctness matters. We're proposing an application where the vector lengths can be quite long. For expressive instruction sets like the EVM, Ethereum Virtual Machine, that include things like hashing or signature verification, these can be over 1 million constraints. And the insight in how we're able to build a succinct vector lookup argument comes down to a neat trick in how to encode vectors within polynomial commitments. So let me explain a little bit about that. There are a few ways to encode a collection of elements within a polynomial. You can encode it as the coefficients of the polynomial, as evaluations. Let me expand a little bit on the evaluation encoding, since that's what we're going to be building on. You can take a subgroup. If we're trying to encode a collection of field elements of size mn, we can take a subgroup omega f star of size mn. And let's say it's generated by little omega. Then we can define the evaluations of f on this subgroup. We can say f of 1 equals f11, f of omega equals f12, f of omega squared equals f12, and f13, and so on to get these mn evaluation pairs. And then these mn evaluation pairs will uniquely define a degree mn minus 1 polynomial f that we can interpolate using Lagrange interpolation, for example. Okay, so I'm going to claim to you that this doesn't provide nice algebraic structure that we can use to work with the vectors that are within this collection F. You can think of this as kind of, this encoding kind of flattens all the vectors into a single subgroup omega. So instead, we consider another slicing of omega, where vectors are instead encoded as evaluations of cosets of omega. Okay, so what's a coset? We can take a further subgroup of omega of size m. Recall m is the length of the vectors. And so let's call this further subgroup gamma of size m and have it be generated by little gamma. And we can show that little gamma must equal little omega to the power of n. And there are going to be n distinct cosets of gamma in omega. So we have gamma, oops, I'm sorry. So we have gamma, we have the first coset omega gamma, the second coset omega squared gamma, and so on. And then we have these n cosets of gamma that span the subgroup omega. And then we can encode the vectors of f as evaluations over the cosets of gamma in omega. Okay, so this does have some nice algebraic properties that we're going to be able to make use of. But first, you might be asking, why would we expect f star to have subgroups of all these different specific sizes? Now we need subgroups of size m for the instruction length. We need subgroup of size mn for the execution table, of size lm for the instruction set table. Are we going to need to work over some type of like wonky group that's specifically designed to have subgroups of these sizes? Well, no, we're in luck. Popular elliptic curves that we use today have been specifically designed to have prime order subgroup FP with FP star that has subgroups of large powers of 2. So what that means is that for any vector length or table size we want, we just need to pad it to the next power of 2, and we're guaranteed to have subgroups of that size within our popular elliptic curves. And the reason these elliptic curves have been designed this way is for the purpose of performing efficient fast Fourier transforms for Lagrange interpolation, for example. Okay, so we have elliptic curves that we can perform this coset encoding over. Now, why is this coset encoding helpful? Well, here's the main technical lemma from Habak that many of our lookup arguments are based off of. So don't worry too much about the details here. I just want to give a short preview about why this coset encoding provides some nice algebraic structure. Okay, so in this Habak check, we can see that the vectors of f are encoded in the denominator, where they are encoded as an inner product with these powers of a random challenge beta. Okay, so as a subprotocol of our coset lookup argument, we're going to, it's going to be useful for us to build up a polynomial I that encodes these powers of beta, 1, beta, beta squared, all the way up to beta m minus 1, in each of the cosets so that they're aligned with the vectors f within the polynomial f. This is going to be useful later because we're going to use that kind of, the fact that they're aligned is going to be helpful for us to do this inner product and compute this Habak check. So just to give you a flavor of what the algebraic properties of the coset encoding gives us, let's look at how would we build up this polynomial I that encodes the powers of beta. Okay, so we can enforce a few polynomial constraints to do this. We can start with I of 1 equals 1. This just anchors 1 into this first position. Next, we can set another polynomial constraint over gamma. Okay, so what is this constraint doing? On the left-hand side, we have these two expressions. What the constraint is enforcing is that for every element in gamma, for this constraint to hold, one of the two expressions on the left-hand side must be equal to 0. So let's look at that first expression. It's saying what? I of gamma x equals beta times I of x. So what is that enforcing? That one thing it means is that I of gamma equals beta times I of 1. So that puts beta into this second position. It also is enforcing that I of gamma squared is equal to beta times I of gamma. That puts beta squared in the second position, and so on. We can fill out the powers of beta. What that second expression is doing is just a stopping condition. It's making sure that we're not enforcing that beta to the m minus 1 times beta equals 1. Okay, so we put the powers of beta into the first coset. Next, we can have another polynomial constraint here over omega. Let's look at the first expression on the left there. So that's saying that I of omega x equals I of x. What does that give us? Okay, so one thing it gives us is I of omega equals I of 1. We're setting the first position of the second coset equal to the first position of the first coset. It also is saying that I of omega gamma is equal to I of gamma. So it's saying that the second position of the second coset is equal to the second position of the first coset. And it's also saying things about the other cosets as well. So it's saying I of omega squared is equal to I of omega. The first position of the third coset is equal to the first position of the second coset. Okay, so what's it doing? We're copying all the values from the first coset into the other cosets as well. So This is, again, just a flavor of why these algebraic properties of the coset encoding is helpful for us. Little gamma, the generator for gamma, allows us to make polynomial constraints that talk about things that happen within a coset. We can make constraints for properties we want for within a coset. Little omega allows us to traverse across cosets and make constraints about how cosets relate to each other. So altogether, to complete the coset lookup argument, we end up just building out a few more of these polynomial constraints. I'm not going to go into the details here, but please refer to the paper if you're curious. And so these cosets allow us to build these polynomial constraints in such a way that we can do this Habak check, essentially. And then the last thing I'll say here is that then we have kind of standard techniques once we have this set of polynomial constraints to retrieve a succinct argument of knowledge after that, using polynomial commitments and polynomial evaluation opening proofs. Okay, so with that, let me start to conclude here. We designed a new succinct vector lookup argument as a way to improve prover efficiency for machine computation. I briefly described this coset encoding, which we use for multiplicative subgroups when encoding a univariate polynomial. But we can also extend these techniques analogously to polynomials and proof systems over multivariate polynomial commitment schemes, where values are encoded over the Boolean hypercube. And so we can, again, encode vectors as subcubes over this Boolean hypercube. And we can build a succinct vector lookup argument in this case as well, where there are more prover efficiency benefits as well. So we have an implementation of the univariate coset lookup argument that I would encourage you to take a look at and play with. We show that it results in prover efficiency gains for machine computation. So with that, I'll conclude, and I'm happy to take questions.
Nice presentation. We have time for some questions.
You mentioned this is more efficient than using recursion. Could you say more?
Yeah, so actually it's not as cut and dry as more efficient than recursion. It's not quite so clear which one might be better. So recursion adds overhead in certain ways, but it also reduces our modern recursive approaches, which are using folding techniques, also remove prover overhead in ways as well. So it's not quite clear what the trade-offs would be. I think there are pros and cons of both. One thing that is beneficial about our approach is that we can also open up prover efficiency benefits of polynomial commitments that work over multivariate polynomials and make use of our prover efficient error correcting code techniques. Typically, our folding techniques for recursion make use of homomorphic polynomial commitments, which incur slightly more prover cost, among other things. Yeah.
Thank you for your talk. I wanted to ask what are approximately the sizes of the subgroup generated by the other generator? What was the gamma? So like, are we talking? Yeah, can you give like approximation of which size we're talking about? Is it like 2 to the 15 in both directions, or the gamma coset can be like significantly bigger?
Yeah, big. So gamma, the coset of gamma is sized to be the size of the number of constraints you need to describe an instruction.
So in practice, this is like thousands, right? You mentioned so for the VM implementation for Ethereum, that would be like thousands. You don't really need it to be like significantly big.
Sorry, say that one more time.
You don't need the subgroup generated by gamma to be, I don't know, big to the 16. It's fine if it's like a few K. Like the realistic size of that second subgroup is about several thousand.
You're talking about gamma or omega?
Yeah, the subgroup generated by gamma.
Yeah, so the subgroup of gamma is, so like it said, it needs to be of size m, the number of constraints needed to describe an instruction. So for EVM, which has instructions that have like hashing and like very complex instructions, gamma would have to be quite large, it would have to be over 1 million. But for simpler instruction sets like RISC-V, for instance, we could set gamma to be of size like 128 if we're talking about 32-bit operations.
Yeah, perfect. Thank you.
Then let's thank Narvin again.
Sure. Or
there is another question. There's another question. Sorry.
Great talk. So how does the prover cost scale with the execution step? In the last summary you said, like, was the asymptotics?
Say that one more time, sorry.
So in the summary slide, can you, yeah. So you said that prover cost scale with the cost of executed instructions. So what's the asymptotics, the relation?
Yeah, so the asymptotics would be, okay, so if you have the number of execution steps n, and each instruction can be described by constraints of size m, then the asymptotics of the protocol are O of n times m plus L times m, where L is the instruction set size.
I see. So it's linear basically.
Well, okay, so that depends on the on whatever polynomial commitment scheme you end up using to instantiate it. So if you want a constant size proof, then we would be using polynomial commitments like KZG, which
Right.
would incur a logarithmic factor on top of that.
Right.
Otherwise, you could also have linear time polynomial commitment schemes as well. Yeah.
Okay. Thank you.
Then let's thank the speaker again. And we have the last talk of the day. It's about rock, paper, scissors, toolkit for lattice-based succinct arguments. And this is a work by Michael Kloss, Russell Lai, Ka Nguyen, and Michael Osadnik. And Michael will give it a talk.
Thanks for coming. Thanks for coming to this very last presentation. So yeah, the topic of this presentation is rock, paper, scissors, a toolkit for lattice-based succinct arguments. So we already heard pretty much about proof systems. So let me start with a very quick and informal introduction. What is actually an argument system? So what is the objective of argument system? The goal is to derive a protocol such that the party can prove the knowledge of witness to some NP statement. Particularly in our case, we are interested in a very specific NP statement, which resembles a cis instance. So we have a matrix A, and also we have an image V, and the witness to the statement is a vector U, so that A times U is equal to B. Further, we impose additional requirement that this U needs to be short, that it needs to be bounded by some the norm of this vector needs to be bounded by some beta. So one can we just send the vector U in plane and call it a day? Well, unfortunately, we have some values objective we want to meet. So, for example, witness may contain some sensitive information, so we would like to keep the witness secret. Also, maybe sending the witness in plane is insufficient due to the communication succinctness. We would like to keep the communication sublinear in the size of the witness. And also, we would like to keep the verifier short. The verifier runtime succinct. Potentially, verifier is operating on some restricted device. So even reading the witness might be already impractical. So let me draw some very broad and not exhaustive landscape of lattice-based argument systems. So those are all work from past years. And within this family, we can identify some subfamilies of argument system. So some argument system only support some argument systems support a succinct verification. Some argument system only support a restricted family of structured relations. Those typically tend to have the most concrete efficiency. And also we have some family which are not argument systems themselves, they are polynomial commitment, but then those can be turned into argument system via generic TCP transformation. Further, within this family of structured relations, all of those protocols can be described as folding-based protocol. And now let me give you some intuition about what is folding-based protocol. So in a very high-level idea, folding-based protocol is folding is about turning a relation which is large into a smaller relation, so that the witness to this smaller relation can be just sent in plain and can be succinctly verified in plain. However, with this kind of protocols, we typically face with a problem that the relation that we are proving is degraded, which means that this is too weak in some applications. To be more precise about this, let me give some preliminary, some background knowledge. Let's start with defining a reduction of knowledge. Reduction of knowledge is a pair of arguments corresponding to prover and verifier, which interactively turn the relation from Xi0 to Xi1. We define the following properties of reduction of knowledge. First, we say that the reduction is correct if it indeed reduces the correct input statement in Xi1 into from Xi0 into 1 in Xi1. And further, we define a property which we call relaxed knowledge sound, which means that after seeing the statement in Xi0 and while interacting with the prover, the algorithm, which we denote as extractor, can recover the witness to the relation Xi0 from the relation Xi1 by interacting with the prover, but potentially running the prover multiple times. And here I say that I denote this relation as Xi0 KS and Xi1 KS because potentially this is not the same relation. It might be some relaxation, which is typically just a bit larger bound of the witness. And if we talk about like a more traditional language of argument system, those properties correspond to correctness and extractability of an argument system. And folding-based protocols, or almost all, I think all argument systems can be used as a series of reduction of knowledge. So now we are ready to talk about the issue of which I highlighted 2 slides earlier. So let's start from a simple relation. We have matrix A, we have witness W, and we have some image, and then we interactively turn this relation into smaller and smaller until at some point the witness is so small that it can be just sent in plain. However, if we consider this kind of folding, this is the folding which for example can be captured via CLM23 paper. If we observe what happens to the norm of the witness, with each round of this folding, the norm of the witness gets degraded, it's getting worse. And further, at this point, if we would like to run the extractor, we see that with each round, the extraction also makes the norm of the witness larger. Effectively, we ended up in a witness which has the norm which is significantly larger than the original norm of the witness we started from. And now we have those two, we call those 2 gaps. We know those gaps as correctness and knowledge gaps. And the consequence is that instead of proving, as I said, instead of proving the relation of Xi0, we prove only some relaxed variant of this relation. And more importantly, this relation in Xi0, if you want to make some cryptographically meaningful protocol, it still needs to be, for example, hard and which impacts drastically the parameter selections. So now, with this background knowledge, we're ready to state our research question. Can we design a series of reduction of knowledge which fully eliminates correctness and knowledge gaps? Within this work, we give an affirmative answer to this statement. We indeed define the lattice-based series of reduction of knowledge with no correctness and soundness gap. And further, we have some auxiliary results that some additional toolset that we defined. We defined a new subtractive set over composite cyclotomic rings. We defined some new inner product embedding techniques and succinct consistency proof of CRT transformation. However, in this presentation, I will focus only on the first aspect. Before I can overview the protocols themselves, I want to define the relation that we are actually operating on. As I said, this is kind of structured relation. So we have some statement and witness, and we have the almost regular cis relation, which is operating over some cyclotomic ring. However, for the sake of this presentation, this is VQ is enough for us. Also, we require the witness to be bounded by some norm beta. And further, we say that the witness is not necessarily a single column. It can be multiple columns, which will be useful in our reductions of knowledge. And also, we require the relation to be structured so that each row has a row tensor structure. Namely, each row is a tensor of some row vectors. With it, so knowing this relation, we can. I want to overview our protocols. Our algorithms. So both our algorithms are split and fold, which are, let's say, almost fold-core construction for reducing the witness size for this kind of specific structured relations. Further, we have a decomposition, which is a standard decomposition with some radix, which shrinks the norm in the correctness direction. And also we have our non-check protocol, which is, I would say, the most theoretical contribution of this paper, which serves as an intermediate opening to the norm of the witness in such a way that it acts as an upgrade in the extraction direction, so that during the extraction, we indeed upgrade the norm of the witness. Let me suggest some combination of those protocols. So maybe first you can execute non-check, then decomposition, split, and fold. And let's observe what happens to the norm of the witness. So first, we pay some cost for execution of the non-check protocol. However, these costs get compensated by decomposition so that we get lower norm of the witness. Further, we have split and fold, which again slightly increases the norm of the witness. However, we end with the same norm of the witness that we started. And what happens in the knowledge soundness, in the extraction direction? So in each of those protocols, we gain some cost. However, within the non-check, this cost can be again upgraded to the original cost. Therefore, in both directions, we start and end with the witness of the same norm. And further, this series of reduction of knowledge is repeated multiple times, so that we can also take advantage of reducing the dimensions of the witness. So let's observe what happens. So we already see what happens in the norm of the witness. Let us observe what happens to the dimensions of the witness. So again, we start from this cis-like relation, and in each step, we reduce the dimensions of the witness due to the split and fold protocols, so that at the end the protocol can be the witness can be sent in plane. So with this high-level overview, I think let me now try go through each of those protocols, at least informally, one by one. So first we have this split protocol, which takes this very large relation and splits it into two, so that it is so that the witness is split into two parts, which are then combined horizontally. This is possible due to the tensor structure of this matrix A. And further, the right-hand side has to be recomputed, sent to be verifier, which checks the consistency of this split. And correctness and knowledge soundness follows almost immediately, as we can see that in both directions this is simply rearranging of the witness. The next reduction of knowledge in our series is fault. So we had this relation which is given to us by split row, and now we multiply both sides of the equation by some challenge matrix, which is sent by the verifier, which combines the columns of the witness, so that we again end with the witness which is smaller in dimensions. And now we have again the correctness and knowledge soundness, which is very similar to known techniques, for example, from CLM 23. And with this, with those two reduction of knowledge, we can now talk about those two additional ones that we introduce. So we have the decomposition, which is the composition via some radix. So, for example, we can take a matrix and decompose it via, let's say, binary radix, so that we indeed reduce the norm of the witness. And since this is very easy work, I can give the algorithm explicitly. So we have the regular shape of our reduction of knowledge. We have our prover and verifier, and the prover takes the witness and decomposes the witness with respect to some radix speed, and further the prover recomputes the right hand side, which is now sent to the verifier. The verifier checks the consistency, and upon checking, we end up with a new relation psi1, which is where the witness has indeed smaller norm. And again, the decomposition is correct and knowledge sound, because like, the witness can be combined and can be decomposed and freely recombined. So now let me talk about I think the most interesting and the most challenging reduction of knowledge out of those four. So let me start with some easy observation that the inner product of two vectors can be viewed as a squared 2 norm of this vector. I'd say it's almost true because it's not fully true if we operate on cyclotomic rings. However, this is true after some massaging and applying some algebraic tricks, which I don't want to go into now. And also in this presentation, I will assume for simplicity that now we are operating on a vector, not on a matrix, but these techniques extend pretty naturally to the matrix. And the idea is just to give the opening to this inner product so that the verifier can verify the norm of the witness. So the first step is to compute the convoluted witness and append this convoluted witness horizontally. So what does it mean? It means that we define a polynomial, we define a polynomial as taking each coefficient of the vector and applying this as a consecutive coefficients of the polynomial. Further, we take the same polynomial with negative coefficients. We call this Lorentz polynomial, and we multiply those two polynomials. And now we observe that in the constant term of this polynomial, we indeed have the inner product. Also, we interpret this polynomial as a coefficient of this polynomial as a vector b, and we denote the consecutive coefficients as bi's. Also, we observe that this vector is symmetric, and therefore we can just focus on the one side of this vector. So we take the one side and append it horizontally to the witness and send to the verifier. Now the verifier chooses a challenge and sends to the prover. And what happens is that it chooses some challenge, and the prover computes a new relation. It appends a row with the consecutive powers of this challenge, and also with negative powers, and also this additional row which helps to extract the constant term. Here we denote the elements on the right hand side as a CW, CW dual, CBR, and CBL, and also this element V0. Okay, let's remember this. And now the step 3 is that the verifier checks the statement about the right hand side. So the verifier checks that CW times CW dual is equal CBR plus CBL minus V0. And also it checks if the constant term is indeed smaller than mu square, where mu square is the claimed norm by the prover. And this is how we obtain our final relation. And why this is true? So let's remember those checks and see why the correctness falls. So honest verifier correctly computes the right hand side. So it remains us to prove why indeed those checks pass. So yeah, we said that it's V0 from the right hand side, y is equal to the inner product of the witness with itself. And now we observe what happens to the multiplication of CW and CW dual. Also, we observe what happens to the right hand side of this check, and we observe that here indeed it ends up being the same. So this is how the check passes, and maybe I leave the details to the in the paper, or I have no time to go through it very carefully. And now in this V0 is the squared norm. So if the norm is indeed smaller than mu, then this check also needs to pass. And the knowledge soundness holds as we argue that we either extract the structured variant of Cs, denoted as VCs, or we extract a witness with a stronger norm guarantee, which is actually what we want. Alternatively, beside the challenge which the verifier sends is some non-trivial root of some polynomial defined by the witness, which is highly unlikely under the Schwarz-Zippel lemma. So yeah, here I have some concrete numbers. So the suggested way produces a small proof size, and we obtain those numbers having some objectives in mind. So we wanted to keep it practical, so the modulus had to be smaller than 2 to the 64. And then we tried to aggressively optimize the proof size for the following instances, obtaining more or less 6 megabytes in all instances. However, there are many ways of combining those reduction of knowledge, and we view it as a strength of our paper that this is not like the only suggested, that this is only a suggested way, and there could be many application-specific ways of combining our reductions of knowledge. Particularly, some of them might optimize for the verifier runtime, for prover runtime, or for maintaining a very low modulus, even 2 to the 40, or even selecting of some application-specific rings. And also, we provide a script for estimation of the concrete parameters. And let me end with a couple of remarks. So I define the protocol in the interactive settings. However, as the verifier is public coin, then it can be turned into a snark via regular fiat family transform. The protocol, I didn't say, but it requires a subtractive set. And in our work, we identify a new subtractive set over composite cyclotomic with a very low expansion factor. And last, in this protocol, I didn't tell at any point, I didn't say about any details about the norm that we are operating, but we are operating mostly about canonical norm. However, we provide results also for coefficient infinity norm, which can be especially practical in some applications. And that's all. Yesterday we published a full version. So please take a look if you're interested. And thank you.
Very nice talk. Are there any questions?
I guess just a question on how you fold in the norm check thing. How does from which set does the challenge like zeta sampled from?
So it's in this one we have two type of challenges. That one is the challenge for folding, and this is a matrix, so that each entry needs to be from a subtractive set. However, we have like a good sumness error because it's a matrix, not a single element. And when we talk about this norm upgrade, then we have the second kind of challenge, which we call particle lemma challenge, and this can be almost any ring element. We only require that it is invertible, but invertible over R2. Like there's no any short requirement.
Okay, thank you.
If I have a quick question, like you mentioned that it only works for like structural relations, and which of the like rocks fades if you don't have a structural matrix? Thanks. There are no other questions. Let's thank the speaker again. And yeah, anyone else? I think conference is over.